Okay, so we were talking about descriptive statistics, and we are going to also talk about graphical statistics today. We are going to solve some examples. We have learned things like the quartile, median, where the 50% of the population is below that value. We have learned the differences between sample median or sample mean versus population mean, population median. So we usually in statistics we don't have information about population, and we do sampling to actually account for these to predict those things. So if you're given a sample, so the book contains, for example, this one. It's about quartiles. Let us compute this. So this is example 814. Let us compute the first and third quartiles of CPU times. So that we have a sample. Usually when you have a sample of numerical values, it's good to order them. Ordering is going to be done in analog and time. After that, you can answer questions like you can, by just using array indexing, you can find the first quartile, the median, third quartile, and if there are any outliers, you may also find them. So how many data points we have in the sample? Let's count. 4, 5, 10, 30. So there are 30 data points in this sample, and so 42 and 43 are at the middle. So you can any value between 42 and 43 is the median. You can say 42.5, or you can choose one of them. Both 42 and 43 are out median values, and the bold ones that are marked here. Let me increase my mouse pointer size. The bold ones that are marked here are the first and third quartiles. So you can also, this, in order to find the quartile, if you look at how the example solves that, it's the 25% of the population. So there are 30 samples here. 25% is 7.5, or in terms of order statistics is the 7.5. So between 7 and 8. And this is 22.5 is the third quartile. Only the 8th element, 34, has no more than 7.5 observations to the left and no more than 22. And this one, no more than 25 observations to the right of it. Hence, the quartile one is this 31. So it's the 1, 2, 3, 4, 5, 6, 7, 8th element will be our first quartile, and the third quartile will be the 15. This is the 23rd element will be the third quartile. So here, as you can see, the rule is that if 7.5 is the count of observations, and the quartile rule is that it should not have more than 7.5 observations to its left. So the first quartile, the 20 or the 25 percentile, is basically saying that there shouldn't be more than 25% of the population to its left. So there shouldn't be more than 7.5 elements to its left. If we have chosen 35, there are 8 elements to its left, so it wouldn't count. And also, there shouldn't be more than 75% of the population. There shouldn't be more than 22.5 observations to the right of it. So if we had chosen 30, there will be more than 75% to its right, to the right of 30. So the only element that satisfies this is 34. So it doesn't have more than 7.5 elements. If you count, there are 7 of them, right? Less than 7.5. If you count to the right of 34, there are 22 elements, not more than 22.5. And therefore, 34 is the median. So the formal definition of that is or median, the same thing for median, for example, there shouldn't be more than 50% of the elements to its left and more than 50% to its right. So, so this is 34 is that 25 percentile or the first quartile, and 59 becomes the third quartile. So what is the interquartile range? Interquartile range will be the difference between these two, which is 25. So 25 will be our interquartile range for this example. And if we learned some rule to detect outliers. By the way, just a word of caution, there are different methods to detect outliers. If you see in different places, for example, outlier detection methods that use the standard deviation, assuming the data is normally distributed. Sometimes we may also say, for example, 3 standard deviations, more than 3 standard deviations above and below the mean, we name them as outliers. So that's another rule, okay? So the rule we have talked about, the 1.5 interquartile rule that we have talked about last week, is just one of those rules, which is used a lot. There are rules that are also not based on standard deviation, based on other statistics. But yeah, if unless otherwise specified, you're going to assume the main rule that we have learned in this class is this 1.5 interquartile rule, which is like somewhere 2 pages down here. I think after standard deviation, after standard errors, interquartile range comes after that. Yeah, detection of outliers. So this 1.5 interquartile rule, that's like one of those rules of thumbs for identifying outliers. So if we apply that to this example, interquartile range is 25. So 1.5 times interquartile range, it's 30. So 25 plus 12.5, 37.5, right? So 37.5 is the interquartile range. So you go 37.5 to the left of 34, which gives you minus 2.5? Yeah, something like that. So it gives you some negative value. So 37.5 is larger than 34. So you go 1.5 interquartile distance range to the left of the first quartile, which gets you to minus 2.5 something. And there are no data below that point. So there is no outlier to the left of this first quartile. And if you do the same thing, 37.5, if you add this to that, it's something 90 something, right? So if it was 60, it was 97 point. So 96.5. So 96.5, if you add 37.5 to the third quartile, you get 96.5. So any value above that will be an outlier if we use that rule. And we have such a number here, right? This 139 is above 96. So it's, as you see, we have one outlier. So this 139 seems like an outlier in this data set. And if you do the median, for example, if you 42 can be a median, not more than 50%. So 50% is exactly 15 elements, right? So to the right of 42, there are 15 elements. It's not more than 15. So 42 qualifies for a median. And there are less than 50, there are not more than 50% of the data to its left. So you can say 42 is a median with no error, because exactly 50% lies to its right and less than 50% lies to its left. So the rule is no more than 50% should lie to both of its sides. So that 42 qualifies for that. 43 also qualifies for the median because to the left of it, there are exactly 50% of the numbers, 15 of them. And to the right of it, less than 50%. So 43 is also the median. So 42 and 43 is the median. You can say that for this example. When we have an even number of data points in our sample, we can choose either one of them as our median. All right. I mean, if you're going to pick one as an integer, if you can also say 42 point, it's not one of the, since 42.5 is not a data point in our sample, if we are to choose a data point from our sample as the median, we have to choose either 42 or 43. Both will be fine. All right, so this was median, quantiles, quartiles. We haven't talked about sample standard deviation. I'm going to talk about that next. And each time we draw some sample from a population, when we compute some statistic about it, that statistic is a random variable, because each time we select a sample, we get a different result. And therefore, it has a certain distribution. The general term for that is the sampling distribution. And I gave an example. Sometimes the sampling distribution, when we're computing statistics like standard deviation or average, the mean of sample mean or sample standard deviation as our statistic that we compute, they will be normally distributed because of the central limit theorem. If it says if the statistic we compute is like sums or averages of those data points in the sample, it will have normal distribution. But for certain things, for example, if you use the maximum of a number of a sample, the maximum data point in a data sample, it may not be normally distributed because it's not summation. So it will have a different sampling distribution. We talked about some characteristics about the statistics that we sample statistics that we compute. For example, being unbiased. Unbiased is something that we can compute theoretically without actually mathematically if you know how your sample statistic is computed from your individual data points, and if you know the distribution of your individual data points. For example, if you know the mean, or you don't need to know actually the expected value. All you need to know is that each of these data points, you know that they're identically distributed. If you know they're identically distributed with some mean and standard deviation that you don't know, that's the population mean and population standard deviation. But if you select your sample from identically distributed data points like this, and if you know the formula for how you compute your sample statistic, you can determine whether this statistic is unbiased or not by checking whether the expected value of this statistic is equal to the population parameter. Okay, so for example, we may not know what mean is, but if we know each of these come from an identical distribution, so the expected value of each of these x1 will be mu, if we are talking about the mean, for example. And then we can compute that the expected value of this formula here, because of linearity of expectation, is going to be n times mu. N times mu divided by n will give us mu. So the expected value of this x bar will be mu, which tells us that it's unbiased estimator. Another thing that we talked about was consistency. As the sample size increases, if the difference between the absolute difference between the your estimator and the population parameter decreases, and in other words, if the probability that the difference between them is greater than some epsilon, that if that probability diminishes to 0 as n gets larger, we will have a consistent estimator. Okay. We talked about medians. Another thing we talked about was mean versus median. If mean is equal to median, we have a symmetric distribution. If median is less than the mean, in that case, we have, so just think about it like this, if you don't remember how this rule goes. Mean, in order for the average to the right-hand side of mean, you have to have a heavy tail at the side of the mean. So so if we do that for example, exponential distribution, we see that exponential distribution is also right skewed because its mean is smaller than the average. Its median is smaller than the mean, where the median is 0.6931. This mu is 1 over lambda, which is larger than median. So we have covered all these things last week. So this is, I'm going to skip this one. Yeah, I think we were somewhere here. We also talked about quartiles. We talked about, we just did an example about this. Now, yeah, we can continue with this example 8.15. I think this is where we were. So uh, here in this example, let me read the text 15, the example that is just following up this one. Calculating factory warranties from population percentiles. So a computer maker sells extended warranty on produced computers. It agrees to issue a warranty for X years if it knows that only 10% of computers will fail before the warranty expires. It is known from past experience that lifetimes of these computers have gamma distribution with alpha 60 and lambda 5 years. So what is the, for example, you can compute, for example, what is the probability? It's like we're going to ask the inverse. This is like an inverse CDF problem. So what percent, so in CDF, we are going to do the inverse CDF asking which life, which duration gives me, or less than which duration of the population, or which duration gives me a CDF of value of 0.1. Okay, we have to compute this X, the time, and advise the company on the important decision under uncertainty about possible warranties. Okay, so we just need to find that since we know that 10% of the computers will fail before that time, and we want to issue warranty so that only 10% of the population use that for warranty. So we need to find the time where the computer fail. What is the probability that, let me write it here, the computer is going to fail. So probability this t is less than some t is equal to 0.1. Okay, so we want to find this, and t is this our gamma variable with, so it's gamma with alpha is equal to what it was, 60 and 5. So alpha is 60 and lambda is 5 times a year. Okay, so it's year minus 1. So 1 over 5 years is 1 over lambda. So actually 60 over 5. So it's like 12 years. So the expected lifetime of this computer is like 12 years. 12 years is the expected lifetime. So the expected value of this random variable t, which is the lifetime of a computer, is 12 years. So what we want to figure out is that, for example, if I give the probability that, or less than t, it doesn't matter, gamma distribution is continuous. So we want to find something. For example, if I say, what is the probability that t is less than 8 years? If it's, for example, it turns out to be 0.1, then we are going to issue a warranty for 8 years. Because only 10% of the computers fail before 8 years. But what is this? Is this really 8? We need to figure that out. So we need to look at the inverse CDF of gamma. And we can also apply, since gamma, so this alpha is 60, we can also apply the central limit theorem here with expected mean value of 12 years because this alpha is large. Okay, so it's an summation of 60 exponential random variables. So central limit theorem applies here. Let's see whether the book uses that too. Yeah, actually it uses the central limit theorem. So large, alpha is large. So using the central limit theorem, first the mean is 12. We also compute the standard deviation where variance was 60 divided by 5 square, this was the variance. If you take the square root of it, the standard deviation becomes 1.55. So all we need to do is standardize this value, 12. So we are going, which is going to give us so this. If we standardize this, z becomes the 10th percentile that we want to figure out. So we don't want what we know that mu is this one. So the standard value we have here, the 10th percentile of a standardized variable, this one. So this one is the inverse CDF of the minus 1.28. So let me write it here. Get a new slide. So if it was a standard random variable like this, and we do that with central limit theorem, we know that this area is under the curve. The area under the curve to the left is 0.1 for the value of minus 1.28 or 58. What was that? Let me go back at 28. So for the value of minus 1.28, for the z value of minus 1.28, we have 10% of the area, or 0.1 area to the left of it. Okay, so in this standardized variable. So below 1.28 standard deviation of the mean. So it just basically 12 was what we had, the mean. So you want to go 1.28 standard deviations below the mean. Okay, so you just multiply it with your standard deviation, which was 1.55, right? Yeah, this is 1.55, which gives you 10.02. So so you may give a warranty of 10 years. So only 10% of the computers fail below 10 years. So this is how we unstandardize a variable. So the standard z for 10%, we know that is minus 1.28. So we apply this to our variable. So we have to go 1.28 below the mean, where mean is 12, and this time the standard deviation is 1.55. So we go this many standard deviations away below the mean to get ourselves this 10.02. So this uses the central limit theorem to solve this question. Now another thing we have to look at is the sample variance, and here the formula is a little bit different. It's not the average of differences of sample data points from the sample mean. So we have a sample mean, which is actually an estimator itself. If we knew the population mean, we would have used, it would be a better way to compute the sample variance by checking the difference between those two. But the thing here is that we don't know the population mean. Therefore, when we're estimating something here, sample variance, we use another estimator we did for mean, which is the sample mean. This actually introduces some kind of bias, and in order to get rid of that, I mean, the proof that we need to, this is an unbiased estimator, is rather complicated, a little bit complicated, but it considers two cases. But you can still, so here, if you're wondering about this proof, so it's this one. So at the bottom of page 220, so this is a seemingly strange coefficient, 1 over n minus 1. So it's not like the average of differences from the sample mean. It's a little bit larger than the average. If we take the average directly, it will actually estimate the standard deviation a little bit less. The actual standard deviation is a little bit more than that. So this is basically what it's saying, the sample variance by dividing it by a smaller number, we get a larger value for the sample standard deviation. So but we need this in order to ensure that this sample variance is an unbiased estimator of the population variance, which means that, so what does this mean? It means that the expected value of S square should be equal to sigma square. At first, there are two cases that it discusses. First, it just for simplicity, if the population mean was 0, uh, here what we would have is that so here's the proof is actually like half a page or even less than that. So when the population mean is 0, we get variance directly sigma squared divided by n. And if it's 0 here, what we're going to have is, in order to get uh, the sigma squared, the expected value of s squared, the top of this, the numerator, has to be, is going to resolve to n minus 1 sigma square. And if we divide it by n, you'll see that n minus 1 divided by n is not going to be equal to, I mean, we will not be able to get sigma square from here directly. So it uses, the other part is also something similar, but in both cases, I'm not going to go over the details of this proof, but in both cases, we know that this, in order to get the sample variance unbiased, you have to divide it by 1 over n minus 1. Just think about it like intuitively again. You write the sample variance a little bit larger than how you would compute the population variance. When we were computing the population variance, remember we had these individual data points or individual random variables. Their difference from the mean was squared. Right now we don't know the mean, so it's also estimated. So that becomes another degree of causing error. Therefore, we have to make this a little bit larger to make it to make it consistent. All right, so now this is the sample variance. As you see, the sample variance is related to, in order to compute that, we have to compute the x bar, the sample mean too. Now, if we put all these two characteristics together, being unbiased and the standard error that we have. So standard error of estimates is the standard deviation of our estimator, which means that if we take if we sample a number of times and we look at how each of these sample statistics vary, and we compute the standard deviation of that, that becomes our standard error. So standard error, let me repeat, is the standard deviation of our sample statistic, our estimator. Here, the black dots that you see here on this figure are different theta heads that you compute. So each of these black dots is a theta head, which means that it's a sample statistic that you compute each time you select, for example, a sample of size 100. And if you have selected 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different samples of size 100 each, and each time you computed, for example, this theta head, whatever it is, if the values are like this, the standard deviation of these is called the standard error. So you can actually compute the sample, you can compute the sample standard deviation of this theta head, and if it's if they are dispersed like this, it means you have a high standard error. Sometimes it's as large as this one, sometimes it's small as like this one. So it's all around the place. Your theta head, it means that theta head has a high standard error. Another thing is that if you take the average of your theta heads, the expected, I mean, if the theta heads are not centered around theta, so the expected value of theta head is not going to be theta, so it's biased. And you can also see that we theta heads tend to overestimate, tend to overshoot theta. Most of the values are to the right hand side of theta, and therefore there's a bias to the right hand side. So a biased estimator is going to look like this, and with a high standard error. This is another one. This is also a biased estimator which overshoots theta. All the values we get are it's like the expected value of theta head is above the real theta. And this is a biased estimator, but this time all the theta heads, all these dots you see, they are clustered together. Their standard deviation is small, which means standard deviation of an estimator is called the standard error. So the standard error, we have a low standard error, but we still have something biased. So this is the last figure here is our ideal estimator. We want our estimators to be like this. And this will be achieved when we have, for example, a large sample. When sample size increases, the standard error is going to decrease for certain. If it's, for example, if it's consistent, standard error is going to decrease, and we will achieve, as n gets larger, we will have a low standard error for theta hat, and the expected value, if its expected value is theta, it's going to be all the different samples, and all the statistics we compute for these samples will be clustered around theta. So this is our ideal estimator. This is how we want to have our estimators to look like. And if the sample size is small, for example, we can still have an unbiased estimator, but the standard deviation of, or in other words, the standard error of our estimator may be large. This may be the case when your sample size is small. In that case, we'll have a higher standard error, but still these theta heads are, as you can see, are centered around, clustered around theta, in which the expected value of theta hat again is theta is equal to this one. Okay, so these are, we are going to see in chapter 9, we are going to see how we compute and how we estimate these standard errors in hypothesis testing. We are going to need these things because we are going to say that I want to predict something. I want to predict, for example, a probability. And a probability is, and in that case, we are going to say, if in order to have the probability as close as possible to the real probability, how many, for example, samples do I need to take to guarantee that it's between the distance between them? Actually, we are going to see this in chapter 5 when we, towards the end of semester, when we come to Monte Carlo simulation, we'll need to determine what the sample size should be in order to ensure that the difference between our estimator and the theta hat, the probability that the difference between them is less than the probability that it's less than epsilon is large. Okay, we want this as close as possible. So we'll see what the sample size should be, at least the minimum size of the sample size to be, to make sure we are within the actual probability with certain distance. So as I said, we are going to talk about them in chapter 9, 5. But this is just, chapter 8 is just basically definitions. Again, standard error is the variation of our estimator. How varying our estimator is, that's our standard error. So we talked about this 1.5 interquartile range rule. And the final thing that I want to discuss about this chapter 8 is going to be graphical statistics. So any question up to now about this interquartile range or the outlier rule we had here, or anything that we have covered up to now in chapter 8? If there are any questions, you may write in the chat box. So the final thing in this chapter is graphical statistics. And there are different ways to, these are basically visual aids, visualizations of our data to help us understand how the data is distributed, whether the distribution is skewed or not, whether it's normal, whether it looks like exponential. And the most widely used ones are histograms, and box plots are used a lot. Box plots usually show, it's a really box plot, sometimes called whisker plot. I mean, if the box also contains the whiskers around it, it shows you certain outliers that are in the data set. It shows you the interquartile range, the mean, median, So it gives you lots of statistics in one shot, in one visual. And histogram, let's start with the histogram. It shows basically a histogram is nothing but a frequency or count of certain your sample as values. In order to have a histogram, you need to first uh, have a certain divide your data range, the values that the value range that your data points can take. For example, if your data can take values between 0 and 150, we have to first divide this range 0 150 into bins, equal size bins. And the bin size really is important when you're drawing a histogram. And there is no uh, rule of thumb for determining bin sizes. You can try different bin sizes. You may have them, for example, if you have values between 0 to 150, you can have bin sizes of 15, 10. If you have a bin size of 1, what it means is that in each bin, you count how many elements fall into that bin. For example, if your bin size, bin length is 1 in this 0 to 150, you will basically be counting how many zeros are there, how many ones are there, how many twos are there. And because if your sample size is small, if you don't have enough data, many of those bins will be empty, all right? So instead of just counting how many zeros are there, how many ones are there, how many twos are there, if your sample size is small, it will make it better to just count how many values are there between 0 and 10, how many values are there between 10 and 20. So these bins basically, they define intervals, and we count how many data points in our sample fall into that interval. And for example, there are 7 values between the values of, so this is 28, probably, it's like the bin size is 14, I guess. Yeah, here the largest value we get is 140, so it's divided into 10 equal regions. For 0 to 140, we divide into 10 equal regions, with each bin has a size 14. So this one shows all the values between 28 and 42, and between 42 and 56. Whether you're going to include 42 in this bin or in this bin, I mean, when you're deciding on your bin sizes, if they're integer values, whether you're going to do it like this for each bin, okay, for example, from 0 to 14. And the next is from 14 to 28. If you write your intervals like this, what this means is that 14 is included in this bin, 28 is the boundary of this bin, but it's not included. So 28 is exclusive. So the next bin starts at 28, goes all the way to 42. Okay, and the last one is going to probably contain 140 as well. So that you ensure both ends are included. So, okay, you have to decide on where to put those integer values. You can also have something like this. I include 14 in this bin. So 14 is not included in the next bin. So this is also possible. Okay, so you have to just decide on where the boundaries are included. Are the boundaries included in the previous bin or the next bin? So those bin boundaries, you have to decide on something, either this one or that one. Okay, you cannot count. One thing that's for sure is that if there's a value, for example, 28 here, you cannot count it in both this bin and this bin. Each data point has to be counted exactly once, so ensuring that you can put it in either one of those bins. But as you can see, so for example, between 42 and 56, there are 8 data points here. So this one shows you, this histogram shows you how the data is, it gives you an idea about the probability distribution density function, or the PMF, depending on whether this is a discrete or continuous distribution. But after that, if you can normalize this, for example, if you have a shape like this, you can actually normalize the area under the curve to be 1. I don't think this is done that, but if you make the area, if you, for example, you may try to fit an exponential distribution on this one and try to make the area under 1, which will make you infer the PDF, the parameter, infer the lambda of that exponential distribution if you think that exponential distribution fits this data well. In chapter 10, you're going to see a test named chi-square test to test whether, for example, how good these data points fit our exponential distribution. So the chi-square test is a really nice test. It's like a hypothesis. We're going to say, if this was an exponential distribution with lambda is equal to, for example, 1.5, how good these data points fit an exponential distribution with that lambda. And we'll be able to answer this with some confidence with an associated p-value. When we conduct a chi-square test, we'll be able to answer these questions. But the histogram, as you can see, allows you to see the data points. But the bin sizes are extremely important. Look at this. The same data points, the same one here. If we choose a bin size like 1, it will look like this. We don't get the shape of the histogram at all. I mean, it looks lots of empty bins. It's just the noise just stands out here. The noise in the difference in data stands out. If you make 2 small bin sizes, you get something like this. It's not like a nice exponential shape. Also this one, this just looks like decreasing. Maybe it also looks like exponential, but you don't see the increase either. If you have increased the bin sizes a lot, like this one, it's 50, it's also not good. So you just need to try different bin sizes and see whether you get filled bins most of the time and you get some shape. And there is no rule for the bin sizes, by the way. You just need to try. That's the thing about these visual descriptors. Sometimes you have to play with them manually, tweak them to your needs. And the other graphical plot that I didn't see before I taught this course is the stem and leaf plot. It's the same data we had in those 30 data points we had. I think this is the same histogram for those 30 data points in example 814, or it was 815. I think it was 814 or maybe less. So in that example where we have seen the 30 data points, which was asking the first and third quartile, it's those same data points. So what this one does is it divides. It's like a histogram. If you look at the stem and leaf plot from sideways, you'll see that it looks like a histogram. It has a shape, but it has more detailed information than the histogram. It just doesn't show counts, but the actual data points are shown here. By choosing, for example, the least significant digit towards the right-hand side, so you just basically divide your number, your data point, either from the least significant digit or least 2 significant digits, depending. This basically determines your bin size. If you divide it by the least significant digit, what happens is that each bin now contains 10, bin size becomes 10. So this is number 9. This is number 15 and 19. So the way you read this is that I have between 10 and 20, I have 15 and 19. Between 20 and 30, the data points are 22, 24, 25. So the left out least significant digit is written on the right hand side one by one. So I have 30, 34, 2 35s, 2 36, 137, and 138. So between the values of 30 and 40, I have 8 data points. So this one also shows like a histogram. It shows there are a lot of data points between 30 and 40. Okay, so this is called, so leaf unit 1 means that there's one significant digit, least significant digit that you put away to the right hand side of this one. So this was our outlier 139, if you remember, which is right here, and there are some empty bins, as you see, as there are no data points here. So stem and leaf plot. If you have a lot of data points, it will be very complicated, too many numbers here. So usually this may be for small samples. The stem and leaf plot may be suitable, but for very large sample sizes, we usually prefer the histogram. Losing some of the information here, I mean, the leaf and stem and leaf plot also shows how the data is distributed within the bin, how it's distributed. It's also shown here. And the final thing in the last 5 minutes I'm going to discuss is the box plot. It's sometimes drawn sideways like this. Sometimes you see box plots that are from bottom to top. Usually when you're comparing multiple samples that belongs to different, for example, days of the week, you may get a box plot side by side, and each box plot is like from bottom to top like this, where your data points are on the y-axis and the different samples that you compare are on the x-axis. Very good question. In stem and leaf plot, your numbers may not need to be decimal numbers. For example, if you just turn them into in base 2 or in other base 16, if you may have hexadecimal numbers, you don't need to use powers of 10 if you represent your numbers in different. I mean, the thing is that you just divide the number in some digit. If you're using decimals, it has to be powers of 10. But if you just want to avoid powers of 10 and use powers of 2, or if you want to change the bin size to some other power, you can represent these numbers in another base, and that will give you flexibility in choosing a different power. But yeah, that's a good point. I mean, if you're just dividing it with some fixed digit, it means that if you're using decimal numbers, the bin sizes always have to be powers of 10. But you can avoid that by representing the number in another base. So the box plot, it shows a couple of things. The median is shown. So a box is drawn. So here the boundaries, the box is drawn between the first and third quartile. So it shows actually the interquartile range. So the length of this box from bottom to top, if you're viewing it like this, it shows you the interquartile range. In other words, it also shows you that like the standard deviation in this one is small, standard deviation of the sample, the standard deviation. So 50% of your population is in this box. Okay, 50%, not population, sample. 50% of your sample that you collected on Fridays are within this box. So median is shown within the box. I think this is the mean. The median is the line in the box we see here is the median. So it shows if the line is not at the center, it also shows that that 50% is not equally distributed as 25 around in this box. So in these, for example, the median is roughly here, and it also shows the mean of the data. The mean is also shown as this cross here that you see here, like the crosshair. Let me see whether I'm afraid that I don't want to confuse which one is the median and mean. So is the crosshair mean or the median? Let me go back to the book and confirm that. So here, parallel box plots. So distribution, the mean, yeah, so I was right. So the mean is depicted with a crosshair. So because it makes sense, right? I mean, intuitively, this is what I would guess if nobody told me which one is mean and median. If the box boundaries are the interquartile ranges, I mean, if the left-hand side of the box is the first quartile, the right-hand side of the box is the third quartile, if there is some other edge or some vertical line that is drawn inside the box, that should also correspond to some quartile, which is the median, like the second quartile, right? I mean, quartiles are shown with these box edges or vertical line segments within the box. So this one, therefore, is the median, and the mean is depicted with this crosshair that is inside the box. Sometimes it doesn't need to be inside the box, right? I mean, if the difference between mean and median, is it possible that mean is, this crosshair is outside the box? I think it may be possible, right? I mean, it's really skewed. It may be, you may think about certain examples in which the mean is. Yeah, it's not difficult to think about an example actually. If you have a one outlier, which is way, way large, like imagine you have a single number which is 10,000 here. Instead of 139, just make that 139 10,000. What will happen? These will not change, okay? Because the median, quartiles, they're just about order statistics. Having a single number of 10,000 doesn't change the order of other numbers. So the bugs will remain the same. And this mean is going to go way over to the right-hand side. So it may be possible because when we're computing the mean, we also consider the outliers. By the way, the outliers are also shown here. These are called whiskers. The whiskers of the bugs extend all the way to and 1.5 interquartile range, I think. So let's see. Yeah, this one we draw line inside. Yeah, the whiskers extend to the smallest and largest observations. Actually, it's not, the whiskers do not extend 1.5 interquartile range. So that's another thing important that I want to mention. The whiskers that you see here, if they extended exactly 1.5 interquartile range, the length of the whiskers at the top and the bottom would be the same, right? Because 1.5 interquartile range is a single number. If you extend from Q1, that size, it will come here, and it will come here if you extend same size. So they will be exactly the same length whiskers. So whiskers are not 1.5 interquartile range, but it shows the largest data that is not deemed an outlier. What we do is we apply the 1.5 interquartile range rule to determine the outliers, and any data point that are not outliers, we extend the whisker all the way until the last data point, the largest data point, which is not an outlier. This one too, it extends to the data point which is not an outlier. So we know that roughly 25% of the population is within this whisker and 25 here. And actually it may be less than 25% because we have some outliers here. Okay, so it shows lots of things. It shows how the extent of your data, how large it goes. It shows certain outliers as these dots, which are beyond 1.5 interquartile range if you have such outliers. So yeah, that finishes chapter 8. I'm not going to talk about scatter plots, which is just if you have two variables, it's you just plot it, x variable here, the y variable on the y-axis, you just put your data points. So that's something we use a lot then in Excel, so I'm not going to talk about that. Yeah, box plots, stem, leaf plots, and histograms are what you should know. And as I said, box plots are really useful, shows lots of things about data, outliers, the extent of the data, mean, median, interquartile range, first quartile, third quartile, everything is shown in a box plot. All right, so that's it from me for today. I will stop recording now.